So welcome to TADS. We're very happy to have Jaiung Jun. Did I say that kind of right? Yeah. Okay. Here to tell us about hyperrings and hyperfields.
Thank you for the invitation. So I will probably talk about this new algebraic object, which is called hyperrings and hyperfields. And it has, before I actually give you the definition of object, I'm going to give you some motivation which field this guy is connected. So here's the recent paper, Metroid theory. This is work by Baker. I will probably mention the connection briefly, and there's connection with incidence geometry, work done by Konze and Konjani. And tropical geometry by Viro, and quadratic forms by Murray. And then finally, probably I'm not talking about last two, and there's this combinatorial object called association scheme, and work done by G.S. Chang. All right, so these are possible connections which this algebraic object have, and I'm going to now give you the definition. So okay, so first we have this object called canonical hypergroup. To define that, you have a set H, which is not empty, and you have here something called hyperoperation. So hyperoperation is nothing but a function which I treat as a star from H, H cross H to the non-empty subsets of H. So H equipped with this operation is called a hypergroup if, so you have a list of axioms such that, so in this case we are assuming that it's commutative, and you are assuming that there exists unique element 0 such that equals x. Let me just change the notation into addition because we're going to use commutative hypergroup anyway, so sorry. Alrighty. And this is the inverse. For each x, there exists unique element y, which we denote as negative x, such that 0 should be in here. And we are also assuming that the operation is associative in the sense that here x plus y plus z is now union, where t lives in x plus y and t plus z. Because this guy right here is not an element, but is a set. Okay, so, and we have final condition, which is called the reversibility, which called if x is in y plus z, then z should be in x minus y, where x minus y, I mean the x plus negative of y. Okay. So a hyperring is a non-empty set with hyperoperation and usual multiplication such that this guy is a canonical hypergroup, and this is monoid, so it's commutative monoid, I'm going to assume. And these two operations are compatible in the sense that you have this, then you have this. And as in the classical case, if you get rid of 0, and this is a group, then this is called a hyperfield.
Don't you want containment there?
Say again?
Don't you want containment there?
No. So this is usual operation. This is single valued operation. And here you have a set. And these are just equation, equality.
No, I mean a containment instead of an equality. Okay.
Then this is a hyperfield. Right. So it's basically the same as classical rings and fields, but you allow the addition to be multi-valued. All right.
The thing on the left there with the x dot y plus z, does this mean like
You,
x times everything?
yeah, times, yes.
Yeah, but times everything.
Oh, yes. So thank you. I should have mentioned that what this means is the x times t, where t lives in here, as in here. Okay, thank you. All right. So I'm going to make a little remark how it can be different from the classical case. Is that in general, we don't have nice properties. So if you have A, B, C, D, and if you want to expand this, as in the classical case, then you don't have equality, but you only have inclusion. So, for instance, you have this triangle hyperfield. This is by 0. And you have underlying set with non-negative real numbers. And you have usual multiplication. So multiplication is the multiplication of real number. But the addition, so if you want to add x plus y, I'm going to put a circle around. So x plus y, in this case, is collection of z, where z lives in this, x minus y and x plus y.
Do you want dot to be commutative?
Yes, I'm assuming that every object here is multiplicative, commutative.
Okay, so the monoid over there. Is commutative.
Oh, yeah, it should be commutative monoid. Thank you.
Yeah. And also with the remark, that notation there means like all pairs, like a.
No, this is multiplication. Yeah.
But it's all pairs from the first.
Right. Yeah. Right. It can be confusing. So in this case, the example you can easily compute is that. So in this case, if you compute this, then you get 1 and 3. And this being said, if you compute this, you get 1 and 9. And this is a little exercise one can try. This differs from 2 times 2 plus 1 plus 2 times 2, 2, 1, 2, 1. Plus 1 times 1, which is, I compute 0.9. So you cannot manipulate your equation as in the classical case. So, okay. All right, let me give you some more example, which is actually the main examples in the papers. So there is something called Krasner hyperfield. Which consists of 2 points. And you have multiplication, as in the classical case, which is commutative. But now your addition is going to be this. Where I always identify this singleton as this. All right. And we had another example, which is the hyperfield of sines. It simply encodes the information of sines. So you have S, negative 1, 0, 1. And the multiplication is same as the classical case. You multiply this, you get this. And 1, 1, give you 1. Negative 1, negative 1, give you 1. And x times 0, give you 0, all x. Whereas now the addition follows the rule of sines, meaning that if you add two positive numbers, you have positive. Whereas you add two negative numbers, you get negative number. You add positive number to 0, you get the positive number. And you add negative number to 0, you get the negative number. Whereas operation is fuzzy when you add positive and negative number. In this case, you can get all kinds of signs. Okay. So, all right. Where are we? So, next guy, the tropical hyperfield. I'm using this notation T, which has R adjoint negative infinity as the underlying set. And here the multiplication is the usual addition of real numbers. We'll have, whereas you have this addition. So simply taking maximum, if those two are different, and if those two are same, then you have this. And the final example is the real hyperfield. So in this case, I'm using this notation. So this guy has an underlying set R, and now multiplication is the usual multiplication of real numbers. Now the addition is similar to this one, but a little bit different. So it's x if absolute value of x is greater than y. Also, or I think these two are the same thing. And you get negative absolute value of x and x if absolute values are the same, but they are with different sign. Okay, all right. So one example how this hyperfield has been used is, so all right, so here's remark on generalized group completion. All right, so in classical case, if you have a monoid, commutative monoid M, so which is commutative monoid, and there's construction that there exists a unique abelian group G in such a way that if you have any other abelian group H and monoid morphism, then it uniquely factors through this guy. So the problem of this construction is that when your monoid is idempotent, meaning that you add the same thing and you get the same thing. Then it follows from the construction, you can check that this universal group completion becomes the 0. So by doing this, you get nothing. But if you are in the situation of a nice monoid, such as natural numbers, you can sort of see that you get integers by gluing two natural numbers along 0. But so sort of to remedy this issue, there's paper by Simon Henry proves that suppose that M is idempotent monoid, then there exists a hypergroup H, well, I'm using H there, L, such that this comes with this map I, and if you have any hypergroup H, then there exists unique map from here to here. So his construction is actually more general than what I said. His construction agrees with Grothendieck's construction when M is cancellative monoid.
Is I injected?
No, it's just I is a map. I mean, but in this case, yes, because I will see. I will show. Right. All right. So how this work is that if you have this guy is the Boolean semi-field consists of 2 points. So this is semi-field, and the only difference from this guy with the Krasner hyperfield is that now you have 1 plus 1 equals 1, and you apply this Henry's construction, you get this, what I wrote here. So you can sort of see that you glue this guy 2 pieces along 0, but you don't get the abelian group, but you should get something like this. And I want to keep this guy. So another example of such construction is the one they use in tropical geometry. So in tropical geometry, they have this tropical semi-field, which is, oops, I erased. I denote by R marks. So it has underlying set as R with negative infinity And the addition is given by taking maximum, and multiplication is given by the usual addition. And you can easily see that this guy, as a semi-field, is isomorphic to this guy. With now this guy is semi-field with usual multiplication, and addition is still taking maximum. And by applying that construction to here, considering this isomorphism, what you get is exactly this guy here. Okay. So you can sort of cook up, in a canonical way, hyperfield or hypergroup from the idempotent object. I sort of cheated a little bit because I said it here, you make hypergroup out of monoid. But I said you can actually make hyperfield out of the semifield. But it's just something you can easily do. All right. So okay. So final definition I will be giving is a morphism. So that A and B be hyperrings or say hypergroups, then a homomorphism from A to B is a function f such that x plus y. Now, since this operation is a set, sits inside of the outer sum. And 0 maps to 0. And in the case of hyperrings, a homomorphism is a homomorphism of hypergroups as well as homomorphism of commutative monoids. So again, this is exactly the same as the classical case, but you only change equality into the inclusion. All right. So here's the way to another way to cook up hyperrings out of the classical commutative rings. So remark. So if A is commutative ring, then you can take G as a subgroup of the group of multiplicative units of A. Then if you look at the cosets, is a hyper. With the multiplication given natural way, where this square bracket is the equivalence class, you add up to this G, meaning that you look at the equivalence class of Z, where Z can be made out of linear combination.
So I guess technically A cross mod G union 0.
No, I mean, you look at this one as 0 is the orbit which consists of a single point.
Oh, as in terms of the action of G on A.
Yeah. So is this G. So this being said, this guy here is in fact considered by Q, and then you cut out all the signs. And the hyperfield of signs comes from this construction by modding Q. Q mod by positive rational numbers, which is a group with respect to the multiplication. And the previous Krasner hyperfield is actually this construction. K is any field with, I think, element greater than or equal to 3. And in fact, one can say more general thing than this. For M, which is commutative monoid, and if you have classical commutative ring and you have a surjection, then you can impose here the hyper operation in a way that you sort of push forward and then pull back the element like this. All right. So this is pretty much.
I'm a little bit behind here. So is x times y is z? What's z there?
X times y.
Oops.
Is this supposed to be x y?
Uh,
Okay, sorry.
sorry.
Now I'm okay.
He was jumping down to the next line.
Yeah, I was.
I was-
That might be, but I just wanted to ask because I'm on
Yep.
half a partial board away.
Do you mind if I ask you a question in the middle, or do you want to wait till the end?
Sure. Right. You can ask questions now.
Well, I was just, when you started to pick your subgroup of the commutative ring,
Mhm.
I am not very familiar with this, but I was assuming you were going to pick the additive elements of the ring. Not
No,
the units.
So this is.
What happens if you go down that road?
So this is multiplicative group, and then G is subgroup of that.
Yeah, so you're taking what the elements with identity, multiplicative identity in the ring, and taking a subgroup of that. Is that what it is?
So if you have multiplicative group here, then G act on A, and then you can look at the equivalence class. So this is the set of equivalence class under the action of G on A, and that the set of equivalence class now have two operations in this way. That's what is it clear?
Yeah, no, I was having trouble getting a good handle on
A
what
cross
G
is the group of units.
Yeah.
And if you just consider
Right.
n
Right, okay,
multiplication,
so that's what I thought G
then
was. Okay, yeah.
and
Okay.
G might be smaller, but it's a subgroup.
Right, yeah.
All right. So now I'm going to explain some connection, which so the connections.
So in this case, it's number 2, and that one it's all of the units.
Yeah.
Well, that one, it's actually only half the units.
Okay. Yeah, I just wanted to make sure I understood what G was, because I thought I had it and I thought I
G is just randomly chosen
I
subgroup.
get it now. Thank you.
All right. So this is what I said at the first place. So Metroid theory. Oops. Oops. I got only 20 minutes left. I haven't even started. Okay. So Metroid theory. In a word, there exists a definition. Let's put it this way. Of a Metroid over hyperfield in such a way that a Metroid over Krasner hyperfield is usual Metroid, and Metroid over hyperfield of signs becomes the oriented Metroid. And probably, and Metroid over tropical hyperfield becomes a valuated Metroid. Valuated. So there exists a unified framework to interpret all different kinds of Metroid under one given by this Metroid over hyperfield. And this is work by Matt Baker sometime this January. And what he did was using this Grassmann-Placer function, which looks like this chirotop definition of oriented Metroid, or this phytotop definition of phase Metroid, but it's similar to that. And let's. All right. So now this is actually what I like. So, and people actually doesn't know about this connection to incidence geometry. This is by Kunz and Kunzani. So you have here Krasner hyperfield, and suppose that you have extension of that in the sense that E plus E becomes 0E, all E. Then there's nice one-to-one correspondence between this object and the projective geometry P. So roughly speaking, you have here multi-valued addition. So here the point becomes this, and line here becomes this. So line passing through two different points is sum of these two, together with x and y. And the other way around, so this is from here to here, and from here to here. You can make extension of K in such a way that sum of two elements is now the line passing through 2. If two points are different and x plus y is 0x if x is y. So you can go back and forth by using this correspondence, and actually this is so complete classification of these guys is equivalent to this old standing conjecture of existence of non-Desarguesian plane with some nice automorphism group. Probably I'm going so fast. Any questions? So there's this old conjecture, I believe combinatoric people know more than me, that whether there exists non-Desarguesian plane which has simply transitive action of automorphisms or not. But it's unsolved, and this problem is exactly the same as classification problem here under this correspondence. All right, and I'm writing one more because this is fun. So this is by Cohen Das and Jagier, 2008. So even I can state more in easier terminology of this one. This one is exactly the same as the problem of finding a prime number P is odd prime, well actually greater than 3, such that P can be written as n squared plus n plus 1, and any A in Fp can be written as difference of two elements. So written as something like as a difference of two elements of this set, A to the n. A lives in the non-zero here. Okay, so these three problems are sort of equivalent. I'm sort of rushing too much.
Two elements of, so you're taking that element A and you're looking at its powers?
No, so yes. This is powers of element of Fp to the nth power, where n is exactly given in this form.
That's n.
Yeah.
Okay. So then that should be b to the n.
Yeah, it's like the same thing, right? Yeah.
Yeah, you gotta use sunlight rather than.
Oh. Yeah.
That'll work.
Okay. T. Okay. So I really don't have time to explain what I did. Okay. So let's just briefly mention one more connection to the tropical geometry. And so those who know the tropical geometry, I'm going to just give you one example. You can consider polynomials such as this in here. And in this case, the tropical solution of f can be obtained by using the tropical hyperfield I was mentioning, such that 0, AB, where 0 is now in here. So I want to just briefly mention that in the tropical geometry, the definition of a solution is not quite intuitive in the sense that they are taking this corner locus than this. So if you use tropical hyperfield, you can somehow turn their definition into more concrete way or intuitive way. All right. So yeah, vanishing locus, yes. Okay. So, all right. Now talk a little bit about this algebraic geometry over hyperrings, which I call it as hyperring scheme. So question start. So the question which start with this the geometry of field with one element is that can you do the same thing as in the classical case when you have M as a monoid or semi-rings? So what classical theorem does is that if you have a commutative ring, then there exists nice topological space, which is actually locally ringed space X, which is a affine scheme in such a way that global sections of this space or global functions becomes this guy itself. So you start with algebraic object, you attach topological space, and the ring of functions on that space becomes the ring you started with. And when this field with geometry of field with one element started, people were considering this generalized object because there were several reasons. But, all right. And in this case, so if you use these two, then in fact, you can do the same thing. So you can construct spec M when M is monoid or semi-rings in such a way that this. So the question, which is very natural at this point, can we do the same thing? Can we do? A hyperring. So this was one of the things that I worked, and the answer, since I'm out of time, is no in general, because there are a bunch of counterexamples. But yes, if your hyperring R doesn't have a zero divisors. So what you can do is that, so when you construct scheme, there are two ways. You can sort of start with prime ideas and localizations, or you can define or find schemes as the opposite category of commutative rings, and you sort of glue that object by imposing some nice topology. So you can do the exact same thing with these two guys. And what people are interested in this theory, the main reason is that this theory of semi-ring scheme, or some people call it as tropical scheme, actually give you scheme structure to tropical varieties. And I considered a similar question, and I got this answer.
So does that mean it works over hyperfields?
No, hyperrings.
No, but I'm saying is the answer. So does that mean the answer is yes?
Hyperfield is not interesting case, as in the classical case of a field, you get a point. I mean, like your topological space consists of a single point.
Oh,
because
that
it
is no, okay, but okay, all right, yeah, fine, okay, yeah, that's okay.
But yeah, yes.
No, I meant rings like hyperrings over hyper. I mean, I meant community rings over hyperfield.
Oh, to do that, you have to.
But yeah, okay.
Okay, and I will just briefly mention one more. That. So this is the one I'm actually working on these days. So if you have a scheme, say over Z, that what one can show is that this scheme itself can be considered of, if you have category of hyperring schemes, this is nothing but the K point, where this guy here is Krasnow hyperfield. Or in user terminology, you can write it this way. And so I get like 5 minutes or so.
Yeah, sure. You have more than 5.
Oh, cool.
3:15, right?
Should be safe to go to 3:25.
Yeah, easy.
Oh, okay. All right.
There's not a cloak. You can have a break.
No, there is a cloak.
No, there's not. I don't think so.
Oh, is that next? Yeah, there's not colloquium. Go as long as you want.
Yeah.
Oh.
Well, we might want to have a break.
Can I just
We might have a
restart?
break at 3:30
I
to go, like-
rushed too much. All right.
I thought there was a colloquium. No, there's not. I already know.
All right. So
So can I ask a question? So if you take a like a polynomial ring defined over Z,
mhm.
yeah, and then can you just extend that by any hyperfield and get something like if you extend it by a hyperfield, like in some sort of tensorial construction, like a field extension. But can you is there like a like
So-
you know how you have you can do a field extension in that setting? Like can you do a
scalars?
yeah, extension of scale. Can you
That's
do a
actually
Can you do a hyperfield extension and find yourself in the non-zero divisive setting if you started off with an irreducible variety?
So-
if you had an irreducible Z scheme, can you like extend scalars like to a hyperfield and like get something nice?
So in general, there's no framework for the tensor of two hyper object, whereas you have a little bit of result. When you have a classical object, you tensor. So I think this is.
In the setting I said, I don't think you really need. I mean, the setting I said, I don't think you really need a formal tensor, right? I mean, you have, you have formal symbols, and then you have like relations.
Right. So
you just like, just allow your.
there's result.
coefficients to be something.
If I remember correctly, there's result by Konze and Konzani. And something of this type, if you have polynomial, say, over T, then you sort of tensor this guy with, say, Q, Krasnow hyperfield. Then what you are getting is
That's the one I care about anyway. Krasnow.
this. And whereas if you do with this guy, then you sort of get this guy. But their method is not concrete in the sense that they don't actually prove anything categorical. But they sort of used this as sort of half definition and half proposition in their papers. But in general, there's no framework as you mentioned. I haven't ever seen it. All right. So the question I was trying to address here is that now go back to the case. Keep this in mind that in the situation of X as a fine algebraic group scheme over some field K, then in this situation, underlying space of X itself doesn't have any algebraic structure. Whereas, so this becomes a group when you consider this guy.
What's is that crescent? Is that the,
No, this is classical field.
oh, it was just the field. Okay.
So you may consider this guy as the homomorphism from A to L, where A is the global sections. And then now this guy becomes a group, right? So when you have a fine group scheme, then you have to look at the rational points to get a group structure. And now you have this identification. And natural question you may ask is that in the perspective of this, since any affine group scheme itself can be considered as K rational point, where K is Krasner hyperfield, is a hypergroup. And just in case, so in the classical correspondence here, the group operation is given by if you take F and G here. So since the opposite category of the affine group schemes is the Hopper algebra, you do operation as you multiply, you compose it with tensor, and here, where this guy here is coproduct of A. And you can ask a question such as, is this same thing in this situation? I'm going to give you which hyper operation you have here, because you have canonical hyper operation which induced from this Hopper algebra structure. So in this case, you have home AK, which is, this is actually theorem, same as in the classical case. You can actually write it this way, or one interpret this as the functor spec is representable by this object. Right. So if you have 2, then your hyper operation, say star is H such that H alpha lives in F alpha 1, G alpha 2, or decomposition of alpha. And this is exactly how you get the here. So this gives the hyperstructure here, and then answer is this a hypergroup? Is that it's sort of yes and no, because roughly speaking, hypergroup ask you whether it's associative or not, but I couldn't prove this operation is associative, but later it has this weak associativity condition, such that you have this guy, which is a set, and you intersect this guy with this guy, and you get something non-empty, which was the best I could get. It's tough. It's tougher than one can simply think. All right. So, yeah, that's all I have to say. And sorry that I rushed too fast.
Let's take our speaker. Do we have any questions?
Yep.
Just a quick question. So this operation, this product of these, you take F and G.
Yes.
Okay, so this describes how you operate on one element. So you apply the co-product first.
Right.
Then you get basically a tuple, and then Oh, I see. So then, okay.
And then you tensor.
I
Yeah,
see.
yeah. And then you can do the same thing, but a little bit different way with this. And then,
Where did the are you assuming it's a co-algebra?
oh, so because I'm assuming X is affine algebraic group scheme, and the global sections of affine algebraic group scheme is the Hopf algebra.
So it's a Hopf algebra.
Hopf algebra.
You don't need the Hopf algebra structure. You only need co.
No, I mean, in this case, the co-product give you the multiplication, and the other structures of Hopf algebra give you the inverse and the identity.
So you need Hopf.
Yeah, I mean, that's the classical case, yes.
So is there a notion of category of hyperrings or something like?
You have object and you have morphisms and you have category, yes. But I cannot say it's good category or not, but yes, category of hyperrings makes sense, yes.
I have a question.
Yep.
I don't know if it's peripheral to that, but looking at x of the of k.
Yes.
K. Can you say that the number of points is the Euler characteristic of the affine scheme over C?
So number of points of which one?
Assume x is actually split reductive.
Mm-hmm. I think that's
So
more or less.
that means x is polynomial count. So its counting function over finite fields is a polynomial in the prime p.
Oh,
So in principle, so then by the Bay conjectures, you let p go to 1, you get the classical Euler characteristic.
that's something.
So that's some sense a way a count of the
Right.
number of f1 points.
Right.
So that looks like a model of f1 to me. So the question is the cardinality of that thing equal to the classical Euler characteristic?
I think to do that, you don't consider hyperstructures, but you have to go to monoid schemes. And there you have some sort of Euler characteristic computation, but which I'm not so much aware of. This is
So what model is it? The model?
monoid schemes. So you have monoid, and then you construct scheme out of a monoid, like commutative rings.
I see. So there's a model for f1 there, like in that setting of monoids?
So, I mean, so F1 model, the easiest case, so F1, they said, is something like pointed monoid. And then the polynomial model is the case when you have this. And so you have sort of projective line in this way. I mean, you can construct the classical construction by means of monoid. You can sort of do the same thing.
Okay, so there's a way to make sense of, you think?
I think people were working on it, but I don't really know because
You don't know? Okay, yeah, all right. But you don't think the hyperfield method gives you that? Or you're not sure? Yeah, okay, anyway.
I'm not sure.
Okay, yeah, it's okay. Anyway. All right, are there any other questions? No? Okay, let's thank our speaker again. Fascinating stuff. Did you turn it off? Very nice talk. Well,
sorry,
very well.
too much.
No.